Hello and welcome to another Data Scholar Code Along. And this Code Along, we're going to do a classification task for COVID-19 using computer vision. The data we have is chest X-ray images, and this should take maybe around an hour, including training time. And what we're going to do is build and train a convolutional neural network in Keras from scratch. And what we will do, we will classify patients as either COVID infected or healthy using the chest X-ray scans. Okay. So Keras is a high-level neural network API, and it was developed with the specific goal to make it easier to build and train deep learning models. It's open source and it's written in Python and it runs on top of Tensorflow. The data set that we're going to be using comes from Kaggle, and it contains about 2,000 images of X-ray data. And that this data set, let me just tell you that, I wouldn't recommend using it for real life diagnostics. This is generally just for educational purposes. Okay. So if you're running in Google Colab, make sure you have the GPU running. So change your runtime to GPU, and that'll just make the training a lot faster. So let's crack on. The first thing we're going to do is import our libraries. So let's do that. So first, from TensorFlow Keras models, import sequential. And sequential is a class we will use to build the model. Most neural networks that we use in TensorFlow will be sequential anyway. And what we basically do is add different layers. It's pretty much pre-built. So all you have to do is define the layers that go into this particular sequential function. Okay. So let's get the layers in. So from TensorFlow.keras.layers, import conv2d, maxpool2d, dropout, flatten, and dense. So basically, the conv2d layer helps with the sharpening, edge detection, and looks for other features that can help the model to learn specific characteristics of an image. The pooling layer helps reduce the size of the data. Reduces the image dimensionality without losing any of the important features or patterns. And then the dropout layer, which is done to reduce overfitting. So it basically drops out some of the neurons in the learning process. And then we have the flatten layer. So the flatten layer transforms a two-dimensional matrix of features into a vector, which can then be fed into the fully connected neural network classifier, which is what the dense is for. Flattening basically converts the data into a one-dimensional array, and then it can be passed over to that particular dense layer. Okay, the dense layer is basically the classic fully connected neural network layer where each input node is connected to each output node. And we basically need a dense layer as they are used to predict the labels. So the next part is to import the optimizer. So from TensorFlow.keras optimizers import Adam. Okay. And then we'll import the image data generator, which is from TensorFlow.keras pre-processing.image. Oops, image, import image data. Okay. So the Adam optimizer is a stochastic gradient descent method, and it's pretty much based on adaptive estimation of the first order and second order moments. If I could go into this in a lot more detail, but what I'll do, I'll put the links to the Adam optimizer documentation in the video description. The image data generator basically allows us to augment the images, and it will basically increase the size of the training data set without actually needing to find any more images. It's quite a simple idea. It'll duplicate images with some sort of modification, so our model can pretty much learn from more examples. Okay, and then we're going to import NumPy as NP for our mathematical computation, and then for the visualization, we're going to import matplotlib.pyplot as PLT, and we'll set the style to ggplot because it just makes things look nice. The next thing we're going to do is import our image data, and it's conveniently stored in a repository on GitHub. So we will steal the images from there. github.com/education 454/datasets. Now, if we run that, too many active sessions. Okay, I've got far too many collabs open, so I've just fixed that. So let's run that, and it'll take probably about 2 minutes to download. So I will pause the video and allow it to download. Okay, they're downloaded. So we can check if everything's gone as we expect it to by checking out the files here. We've got the data sets, data, and here's the test and the train. So we've got the normal images without COVID, and then we've got the COVID positive ones as well. And the same goes for the train. Okay, so let's hide that again. So what we need to do now is basically access the underlying operating system that Google Colab runs on. And it's pretty much called the OS namespace. So we import OS, and what we want to do is set the main directory, and we can get that by opening this, go into data, and copying the path, and put that in quotation marks. And then what we need to do then is set the training directory. And we can do that by doing os.join.path.join. And it'll come from the main directory we've already saved. And then the file within there is called train. We can do that with the test directory as well. So os.path.join main there, and then test. Okay. So what we're going to do now is we obviously have the images stored in subdirectories, so we will also have to define them too. So let's do train COVID here. And you know what? We'll just copy and paste this. It'll make our lives a lot easier. And so what we need to put in there is train here. And then the file name is COVID-19 in all capitals. The test, let's do that. I'll tell you what we'll do to make it consistent. We'll do the normal there, and that will be OS path join again. And it'll be train there, normal. And what we can do the same for the test as well. So we can just copy these two lines, change that to test, change that to test, and then change these directories to test as well. And that should do it. Okay, so let's just get rid of that extra space and we'll run that cell. There we go. Okay, cool. And what we can do, we can just double check everything makes sense by printing the file names contained within these variables. So train COVID names equals OS list there, train COVID there. And we will print train COVID names, and we'll just take 5. There we go. And let's do that again. And we'll do it for normal. So we'll just have to do that normal. And then let's copy all of that and do for the test as well. So we just change all the train to test like so. And that should give us there we go. So yeah, seems to have worked fine. No, it hasn't, because I haven't bloody changed these. Tell you what, there we go. Normal, test, and test. There we go. That should work now. So we should get some normals in there as well. There we go. Happy days. Okay. So what we're going to do now is we're going to see basically how many images we have in our train and test. So this is pretty simple. We can do print total images in training, and then we can put len. So the train COVID names plus the train normal names, and we hit that like that. And that's how much we've got in training. So we can do the same with the test as well. We'll just copy that, and we'll put in testing, and we change that to test, and we'll train that to test as well. So if we run that again, there we go. We've got 1,811 for training, and testing we've got 484. Okay, so next we're going to pretty much do I'll tell you what we'll do first. Where are we? Are we validation? Let's not do the data pre-processing. Let's do some data visualization. Okay, and what we'll do, we'll just make a little 4x4 chart of our images just to see what they look like. So the first thing we do is import matplotlib.image as mpimg, I think it is. We'll soon find out. We'll set our rows to 4. We'll set our cols to 4. We will set the fig to PLT G like that. So the GFC, that pretty much stands, well, it stands for get current figure, and it allows us to pretty much reference the current figure while we're using pyplot. So, okay, the next let's set the figure size, because we don't want it too big. Yeah, we don't want it too small. Set size, and we'll put it in inches, and we'll put 12 by 12. That should be perfect. Okay, so let's define COVID image, and we'll set that to os.path .join, and we want to put train COVID there, and the file name. And then for file name in train of there, and we'll take, let's just take 8. I think that should be okay. And then normal image, we'll just copy the same thing. There we go. Change that to normal. Change that to normal. Okay. And we will print COVID image, and we'll print normal image, because what that will do is also give us the file names within our chart. So let's merge them, and it'll be COVID image pick. What am I talking about? And normal image. Okay. So for I index, image path in enumerate, merged image. Data will be image path split, because what we want to do, because we're in it's in subfolders basically. We want to just get the image name to be just what the image is. We don't want the entire file structure. So what we're going to do is split it by a dash, and it's the images are the 6th in the structure. So we'll put 6 there, and then also 6 there, like so. So let's plot it now. So PLT subplot, we'll put our rows and cols in there, and then the index +1. And then the images that we want to use is mpimg. I think it's imread. We'll soon find out. We want to input the image path. And then we want to set title. And we'll just put test. We'll just put that as test. And then, oh no, sorry. We don't want to set the title. We want to set that axis first, don't we? So let's put axis and then test. Okay. And then we want, let's just test. Okay. Now let's set the title. And the title will be our data. Don't want to do that. Data. And we'll set the font size to 10. PLT. I am show. And it'll be the image. And the CMAP is grayscale. Only because the images are in grayscale. And then we come out the loop and show the plot. So let's take a look. So what's it saying there? PLT is not defined. Oh, I mustn't have run that for some reason. There we go. That should be fine. What's it saying? No module optimizers, because I can't spell. Is that option spell optimizers? Yeah, there we go. So let's hit that again. Oh, what's that? Index list out of line. So is it 6? 1, 2, 3, 4, 5, 6? Yeah, it should be 6. So I know what I've done there. That should be names, not there. There we go. What's it saying? Recognize. Okay, off. Got that confused with the. There we go. Off. Turn it off. Turn it off. Got that confused with the set title because I had set title in my mind, and that should do it. Boom. So let's just let that load. There we go. So here's some of our COVID positives, and here are some of the normal as well. I mean, we can see that there is sort of differences between them. It looks like the COVID-19 seems to have a lot of like clouding in the lungs in certain aspects, and when then in the normal, generally, the lungs look clear. Now this one's that'll be a bit of a risky one because that is slightly cloudy. So yeah, interesting. Okay. So what we are going to do next is the pre-processing and augmentation. And what we're going to basically do is create some new data based on the images we already have. It's very simple, but a very powerful tool to help avoid overfitting our data. If we're in a circumstance where we do have limited data, the chances of us being able to make future predictions is also limited. So, as the saying goes, the less data you have, the less chance of getting accurate predictions. I don't even think that's a saying, and I think I've just made that up, but you know what I'm trying to say. Okay, so let's get started. So first thing we're going to do, we're going to make dgen train, and we'll put the image data generator. And what we'll do here is, I think the first thing we should do is rescale. So let's do that. Rescale 1.0255. Okay. So we're going to rescale by a factor of 1 by 255. And as data that goes into a neural network, we need to basically normalize it in some way to make it more digestible, shall we say, for the network. And with image data, we pretty much normalize the pixel values, and this is done by using the rescale parameter. Okay, the next thing we're going to do is create a validation split, and we will set that to 0.2, which is 20%. And we'll do some other bits as well. Zoom range, we'll put that as 0.2. Feel free to mess around with these parameters, and we will do also a horizontal flip, and we'll do that at set to true. Okay. So what we'll do, we'll repeat this for the dgen validation. That'll be image data generated again. Okay, so we'll do the rescaling again to 1.255. And then we need to do the test as well. So we might as well just copy that, and we'll do exactly the same. We'll copy that, and we'll do exactly the same for the test as well. There we go. Okay, so let's just run that for now. And what we'll do now is what we need to do is basically create the train, validation, and test generators. Okay, let's do that. So let's do the train first. So train gen is the dgen train, and we need to flow from directory, and it will take the train there. We need to set the target size 150 by 150. Okay, the subset will be, let's just make that a space there, training. Batch size will be 32, and the class mode is binary because we're picking COVID or not COVID. So flow from directory, that actually pulls the images from our training directory, and it loads it into the generator by the batches that we've specified. The target size, 150 by 150, is what we want to resize our images to, and that is 150 pixels. So it will be that will be constant over our training, validation, and our test as well. Okay, so let's now do the same. Let's just copy this, and we will do the same for validation. So let's do validation again, and we will do the it'll be from the train flow train. Yeah, we'll change that validation to binary. Perfect. And what we can do is exactly the same for the test, and we will take that from the test. Okay. Oh, we need to put that as validation. My mistake. And we don't need the subset here, so we can remove that, and we can change that to test as well. So what you'll notice, that both of these particular generators, they're being loaded from the training directory. The only difference is one uses the training subset while the other uses the validation subset, because we've already split it into 80 and 20%, 20% being the validation set. Okay, so let's run this cell. Done. There we go. But why has that come up with zero? Oh, that's, should have left that as train. That's why. There we go. Do that as train. There we go. That's better. Happy days. Okay, so what we want to do now is find our class indices, and we can simply do that by doing train gen.class indices like that. And what we've got, COVID will be represented by a 0, and normal will be represented by a 1. And then further to that, we can basically, well, we'll take a look at the image shape. So train gen image shape, and that will give us there. So here's our images have been modified to 150, 150, and this 3 is the color index. So that just represents 3 colors, R, G, B, which is red, green, and blue. Okay, so that's pretty much it for our data pre-processing and augmentation. Next, we're going to actually build the convolutional neural network. So as I mentioned before, that we just have to define our model, and it will be sequential. Okay, and then all we need to do then is add layers to our sequential function. So let's do that. So model, and the first one we will add is the conv2d. Specify the filters, which is 32, and then we need to specify the size of the filter, which is 5 by 5. Padding will be same, and our activation will be relu. And we also need to define the input shape, and that will be, as we already know, will be 150, 150, and 3. So it's basically 3 dimensions. Okay. So this first part, this first layer, we've added the convolutional layer where we extract the features of the images. So say if it extracts 32 features from the image, and the size of the searching matrix is 5 by 5, and we've added padding as same so we don't lose any information on the image. And then we've added the non-linearity so the network can basically learn more complex functions. So we've added the relu, and we've then added the input shape, which what the model will expect to be input when we actually start training. Cool. Right. So the next part is we need to add a max pool 2D, and then the pool size will be 2 by 2, and I've selected the 2 by 2, and it actually reduces the size to half, but it does this while maintaining the features of the image that were picked up by the convolutional neural network. So when the images pass through the max pool, the image gets reduced, retains its information, and helps reduce the number of parameters, and that ultimately shortens the training time. The next layer is going to be the dropout, and let's just put that to 0.5. It will pretty much, there's a probability that it'll drop 50% of the neurons, and that helps with overfitting the data as well. So we've basically convolved the image, got the features, pooled it, reduced the size, and now what we need to do is do the same thing again. Okay, so we might as well copy this, and we will change the filters to 64. We need to get rid of the input shape, as we don't need that at this particular stage now. We will add another pooling layer, and we will add another dropout layer as well. Okay. The next part, we need to flatten. So we input model, add, flatten, and we don't need any input for that. As I mentioned earlier on, it pretty much takes the 2D input and reduces it to one input for the dense layer, which we will now add. Model.add dense, and we'll put that at 256. Activation equals again. Okay. Now in the dense layer, this 265 is the let's do like that 256. Let's call it 256. That's the amount of neurons in that particular layer. Okay. So now let's just add another dropout. Okay. And then what we need to do is add the output layer, which is another dense. We only want one in this because it retains either 0 or 1, COVID or normal. And again, activation needs to be relu. Cool. And then we will print the model summary. So we can just run that. And there we go. So here it gives us the summary of our model. You'll notice the first dimension of every tensor has a value of none, and that's because the first dimension will always be the batch size, and the batch size is flexible. So, we can pass any number of examples into the batch to the model, and TensorFlow basically says none there, as it can be, any number. Okay, on the conv layer, the input shape 150 by 150, and the 32 is because we created that layer with 32 filters. Again, the pooling layer, we've got 32 filters, and it now says 75 by 75, which basically it's downsampled the image with 32 filters. And then when we hit the dropout, it stays the same. That is just basically switching off the neurons. And if we take a look at the second convolutional layer, we can see that it's taken the 75 images, the downsampled images, and run it through 64 filters, goes to the max pooling, which cuts it again to 37, 64 filters, and the dropout stays the same. Okay, so the flatten layer then comes in, and it basically unrolls this into a one-dimensional vector, and that is 37 by 37 times 64, and that is 87616. And then we've got the dense layer with 256 nodes. The dropout again stays the same, and then our final layer is the output layer, which has either is a binary, so it either gives us a 0 or gives us a 1. Now we're going to compile and train the model. So model compile, and we will set the optimizer here, and it takes the learning rate, which we will set to 0.001. Now you can change this if you want, but this is generally a nice place to start in computer vision. So the loss will be binary cross entropy, because it's a binary project. And the metrics we will want is the accuracy. Okay. So every epoch that the model will run on, it'll basically, it'll calculate our defined loss and evaluate it. So it'll basically, this particular compile will keep track of these metrics as the model runs and trains. So what we can do now is basically set our model to train. So let's just compile it. Days, and so we will train it now. So we'll set a function history, or a function, a variable, and we'll put model fit, and we'll fit it on our training data. Actually, and we'll set the epochs. Set that to, let's call it 50. Let's try 50. Again, you can increase that, decrease it, experiment with it. Validation data that we want to validate the model on comes from the validation gen that we defined earlier. So the difference between a epoch and a batch size, let's just say we have 1,000 images and we want to train our model on that 1,000 images. We'll say our batch size will be 10, and what that means is that 10 images will be passed into the network one at a time in each given epoch. And an epoch is a single pass of all the data to the network. So if we've got 1,000 images with a batch size of 10, it'll take 100 passes to make a full epoch. Okay, right. So let's just run that and start the model training. Oh, what's it said there? What have we got? Well, no function binary cross entropy. Oh, it's because I've spelled cross entropy wrong. Me and my spelling. If you tune into these quite regularly, you know my spelling is absolutely terrible. There we go. It's running. So this takes a little while, probably about 5 to 10 minutes. It depends on what you've set your batch size to, and it'll also depend on your epochs as well. So as we can see, it's running through the first epoch. We're getting the loss and we're getting the accuracy as well. Once the epoch has run, it'll then display the validation loss and validation accuracy. So let's just wait for a couple more seconds and we'll see what the validation loss and validation accuracy is. And when it moves to the next epoch, it'll put that information here. There we go. So our val loss on the first epoch is 4.5 and the val accuracy is 0, well, nearly 70%. Okay, so I'm going to pause the video. I'm going to let this run and we'll jump back and we'll be able to pretty much evaluate our model. We'll plot the loss and accuracy as well as the val loss and the val accuracy. I've just stopped the training because I've realized I've made a fatal error in my over eagerness to copy and paste. And I hope you spotted it, but this should be sigmoid because it's a binary output. So let's start that again, shall we? Let's compile the model again. I'll have to run that again. Compile the model. Oh, has my Google crashed? It has. So let's just run all that again. The joys. So let's do all the pre-processing again. Sequential, and now that should work fine. Schoolboy error. Compile. And let's start the training again. And I've changed it to 30 epochs because as it was running, I noticed 50 was going to take a long time because each epoch was taking between 30 and a minute. So that's no good. So we've started that again. Let's wait until the training finishes and we'll get back to it. Okay, we're back after that right kerfuffle. So we've run it for 30 epochs. So what we can do now is plot the performance basically and evaluate it. So what do we plot? What we can do is have a look into our history keys. We take a look at that, and what it will bring up is the keys of what the metrics we've measured. So the loss, the accuracy, the val loss, and the val accuracy. Okay. So all we need to do is basically what we'll do first. We'll plot the loss versus the validation loss, and we can do that in Matplotlib, so it's quite easy. PLT plot history, and we extract the loss. The next line, plot history, and we extract the val loss. Okay. And then we will add a legend, and that will be the training, and it will be the validation. Can I spell validation? And the next bit will be the title, and we will call it the training and validation loss. And the X label will be the epoch. Okay. Run the cell. There we go. So the validation, that is, why did it autocorrect to that? There we go. Bingo. So what we're looking at here is the comparison between the training and validation loss. So as you can see, it's fitted the data quite well, keeping both the training and validation loss to a minimum. So the next thing we can do is plot the training and validation accuracy, and we can just take this code, paste it there, and make a few adjustments. So what we want here is the accuracy. What we want here is the val accuracy, and we can just change that to accuracy as well. We will run that cell. And there we go. Done. So the accuracy is increasing as the training goes on over the epochs, and when we get to the end, we're looking at what, 97, 98 maybe for our validation. So it's a pretty good model, but we still need to train it on, or let it predict on unseen data, which we'll do that in a moment. But first, let's just get the figures for it. So all we need to do there is test loss, test accuracy, and we will evaluate and the test gen. And then we'll print test loss, test accuracy, and then we will do a format. And what we want in there is the test loss and the test accuracy without the plus sign. There we go. If we run that, let that run. There we go. And on the test data, pretty good. We get a test loss of 0.107, accuracy of 95. So it's very good accuracy for the test set. But that's nothing. What we need to do is predict on unseen data. And what you can do for this is, what we're going to do is upload some images that I separated earlier on. And we'll upload them and have the model predict. So we're going to import Google Colab, import files, import Keras utils as image, and for file name in uploaded keys, we're going to put the image path to our home directory, so it'll be content, and it'll be plus the file name of the files that we upload. Okay, image will be our image.load. Image, it is, yes it is, and then image path, target size, we want that to be 150, 150 like the rest of it. Images equals image dot image to array. It takes in the image, and images we want to use our NumPy expand ims images axis equals 0. We want that to be file name. Okay, and then the prediction will be our model dot predict, and it'll predict on the images that we've uploaded, and then print file name so we know what ones they are. So if pred equals 0, we want it to print sample. Actually, let's put COVID detected, and then the else will be print no COVID detected. There we go. So if we run that, upload is not defined, and that's because I haven't defined it. That's why. So uploaded equals files dot upload, and that will bring up a Google Colab upload box here. So let's try that again. There we go. So we take that, and I've got in our projects, we've got the COVID prediction, and then we'll just take all these files that have been unseen by our model, and we will open that up, upload the files, and it'll loop through them and make the predictions. Taking its time. There we go. Boom. So COVID-1, COVID detected, COVID-2, COVID detected, COVID-3. Normal 2, no COVID detected, and normal 2 there, no COVID detected. So it looks pretty good because I already knew that these were positive or negative. So it is, the model has been able to detect COVID in them particular sets. So that's great. We've done very well there. It's taken just over an hour. So we can now potentially put this in some sort of app online through Streamlit or Flask and put it to production, and let people use it and let people experiment with it as well. Thanks very much for your time. It was a pleasure having you as always, even despite my terrible spelling and schoolboy errors. But I hope you appreciate the lesson and you've learned something from it. At least spell better than me is the main lesson today, I think. But thanks very much, and I'll catch you next time.